So, as I mentioned earlier, what are the problems that we face with the vanilla? We call it now as the vanilla RNN, because there are going to be variations that are brought into this. So, we call this as the vanilla RNN. In the vanilla RNN, the component of the gradient that correspond to long term dependencies is small. Okay. So, as I mentioned earlier, when you move from the state t to state 0, the components values are becoming smaller and smaller. So, that is the problem of the vanilla RNN. So, but the short term dependencies are well managed. So, keep note of this. Okay. So, the long terms are becoming a problem, but short term dependencies are well managed. Okay. So, they can manage the short term better than the long term dependencies. Okay. The first assumption that we made, that it should be possible for us to really learn a long term dependency, is gone with the vanilla RNN. So, people started looking at options to really correct that. Okay. So, this is what I said earlier too, right. So, when you start using the particular architecture again and again, you will start finding the problem, and then we start finding alternatives or make some adjustment to this same network, so that we are able to solve the problem. This is how we evolve, and the networks evolve as well. So, now we are going to be looking at another variation in the RNN. This is called LSTM, or long short term memory. Okay. So, where did the problem occur? The problem occurred only in the state where we make the computations, right. When we start making the computations for the state in the unrolled RNN, we have problem. So, is it good enough if we only adjust that particular hidden states, so that we are able to reduce the problem of vanishing gradient? Let us see what LSTM does in that case. Okay. So, in this case, what LSTM has is, it instead of one small computation that we make in that ST, remember that ST, right, which is a hyperbolic tangent of HT, correct. So, we are going to be making some changes to that particular computation. We are going to be replacing that summation units with some memory blocks. Okay. So, we are going to have multiple gates that allow cells to keep the information or lose the information. Okay. So, by doing so, we want to achieve a long term dependency in the network. So, that is the idea, right, and also at the same time solve the problem of vanishing gradient. Okay. So, along with the hidden state vector that we have, you remember HT, right. So, this is going to be replaced by another memory vector called CT. So, this is going to tell us how to condition the values of the U, so that the vanishing gradients problem really disappears in the network. So, in this case, LSTM can choose to read from, write to, or reset all the cell values using the gating mechanisms. So, that means there is a very small computer inside, where it is able to read, write, and then do some reset operations, so that the H values are very well conditioned. Okay. So, in my view, it really creates a well behaved gradient. Okay, that is what we want to do, right. So, when you come back from the teeth state during the back propagation, I want to be able to have a gradient that is very well behaved. So, in my view, the intuition is LSTM really computes that gradient beforehand and then keeps it, so that when you come back, you really have a gradient to have the smooth back propagation mechanism. Okay. All right. So, how does it look? So, it is a little more complex than what we saw earlier. Okay. For some, still RNN is very complex, right, and this still adds little more complexity to the RNN mechanism. Okay. This is one cell that we are talking about. So, we are going to be replacing this as I written earlier, this HT is replaced by the whole piece. Okay. All right. So, as I mentioned earlier, there is a separate memory vector CT that we have. So, we have calculated, assume that we have the previous memory state, and then we have the HT minus 1 previous state of the hidden unit. It connects the input through the matrix W or the weight vector W. Let us call it as QT. Okay. This is our HT, right. So, since we are going to have something else here, I am just calling it as a QT. Okay. So, from here we have 1, 2, 3, 4 and 5 different rather let me put it this way. We have operations here, okay, and then see how these are computed. Okay, let us first find the QT, and then this is our forget gate. I somehow do not understand why this was named as a forget gate. Okay, so, this is a sigmoid function. It takes the value from the previous memory cell. Okay, so, when you come here, so forget gate is computed by using QT and a weight vector that you have here. Okay, and then there is an input cell that is computed using the weight matrix that you have here. This is WI, and then we are computing the new memory here. We call it as, and then this is the output gate. We have another and then each one is connected by either a sigmoid or a hyperbolic tangent function. Okay. And then this one is element wise multiplication, this one, this is element wise addition, okay. This is element wise multiplication. Okay. Let us see what happens with these. So, when we compute the first QT, we now have to compute the FT. What is FT? It is a sigmoidal function. So, when you do the dot product of QT and WF, you are going to be making the values staying between 0 and 1, correct. So, there will be values which are closer to 0, there will be values which are in between, and there are values closer to 1, right. So, FT is computed using that, and then you have translated those values into this form, or you have mapped those values of the dot product into 0 and 1. So, this is a vector of this size with some values. We take the value from the previous memory cell, assuming that it is computed, okay, and then do an element wise multiplication of this. So, what happens when you do an element wise multiplication? Supposing if there are, let us say this is Okay. So, this becomes 0 here, right. So, it becomes like 0.1 to 0.6 and so on, correct. Okay. So, what does it mean? So, we are not really asking the machine to forget this value. So, what we are doing is during the training the weights are going to be coming through the back propagation, and we are going to be adjusting in a way that whether the values really correspond to the target that I am looking at or not. That is what we are going to be doing during the training. Okay. That is what is adjusted, right. When you get the error, you start propagating the error back and then adjust the weight. What does it mean? That means, hey, I have some error values, make sure that the value that you are having in the weight is corrected, so that next time when I compute I get the right target. So, the error mechanism really is making the weights adjusted, so that next time it becomes closer to the real target, right. So, in this fashion when we do this, these values are learnt every time. So, when we do the dot product of this and this, we get some values, and then we will have the CT values as this after the element wise multiplication. So, 0 means certain elements are not really considered for the training. That is what it means. Not every value is going away to either 0 or 1 in this case, right. Some values are retained, some values are going to 0. So, if the values which are very close to 0 would be showing zeros in the vector, correct. So, that means the memory is adjusted in such a way that the values that are coming in through the W and the WF and through FT either retained or lost, right. Again, and then taking the input gate. So, what we do is we want to find out, we want to take the input value like we have done in the previous HT calculation, and then we want to compute the new memory using these, right. And then they both are again multiplied element wise, and then it is added element wise to get CT. Okay, so, that is the new memory that we are adding. So, this is one small portion that we had earlier. So, now it is having an FT, and then this is computed and then added as a new memory, and now there is another one which is the output gate. Okay. Again we take the value of QT, use a sigmoid, and then whatever value that we had earlier decided that should be passed on, right, as the memory is brought back through the tanh, and then the output is combined using an element wise multiplication, and finally, the new HT is computed. Okay. So, this is during the forward pass, correct. So, every time you will see that some values appearing and disappearing because of the element wise addition and multiplication. And then you also should see that these values are now controlled by this sigmoidal function and the element wise operation that we are performing. So, the certain thing that we want to retain will continue to be made available through CT, and they will be pushed, and HT will keep remembering those long term dependency through the application of CT in the process. Okay. Is this clear now? Okay. So, what happens during the back propagation? Right. So, we have done the forward pass. So, when you do the back propagation, the error is computed, there is a difference with respect to the goal target, and that is brought back. When you do that, again all the element that we have computed in the forward pass should be having a derivative, and the value is passed on. So, when you keep doing that, right, the values here in the FT, IT and CT are adjusted by the error mechanism. So, by doing so, by conditioning the matrices because of the error mechanism that we have, we seem to be managing to get a good handle on how HT should transfer the values to the next state and so on. Okay. All right. So, this is the forward pass. I think I mentioned about this in detail there, and these are the equations that we have for the forward pass. First, we use the forget gate, and we have the weight, and there is a bias. In many cases, we ignore bias. In LSTM, it is important that we manage the bias as well. Some people would add the bias as part of the HT, so that it does not show up as part of this. Okay. And then we have the input gate that is computed using the QT and the weight that is connecting the input gate, and we add a bias to that, and then we compute the new memory there using the hyperbolic tangent function, and then we find the new memory. So, now we compute the new state of the memory using the new memory that we have computed using this, and then we compute the output gate values, and then plug in the output gate values along with the new memory state into HT. Okay, and then we compute the state of that, and then we compute the, this is ST, right. Output net output, and then we compute the softmax values, and then do the back propagation of this, so that all the errors are corrected, and we have a stable network